I, myself, Tanuja KM.
This is a 1 month internship in an embedded system. It was a valuable learning experience that provided practical exposure to both hardware and software aspects. During this period, I learned the basic of microcontroller, embedded C programming, and the use of development tools such as MPLAB IDE and simulation software. I gained hands-on experience in interfacing sensors and modules, understanding circuit connection, and debugging errors. The internship helped me to improve my problem solving skills and understand how embedded systems are used in real time application. Overall, this experience strengthened my technical knowledge and increased my interest in the embedded system domain. We learned about the C. C is a powerful and efficient programming language. It is used in the system software, operating system, and device driver. Embedded C is used for microcontroller and hardware based system. It covers program structure, data types, and control statements. Topics include like array, pointers, functions, and memory organization. Storage classes, strings, recursion, and the preprocessor are explained. C knowledge is essential for embedded and low-level software careers. We should know about the embedded system. Embedded system which consists both hardware and software. Other than that, embedded system is a specialized computing system designed for dedicated function with a large system. It has a characteristics like low power consumption, real-time performance, high readability, and specific functionality. It has applications like automotive control, medical devices, consumer electronics, industrial automation. The categories of embedded systems are like standalone, real-time, networked, and mobile. These are the major 4 categories we should see in an embedded system. Next, the major components which are present in the embedded system are like microcontroller and the microprocessor. This is the core processing unit. It consisting of a memory like RAM, ROM, flash, stores program code and data. It has input and output sensor, switches, displays, and actuators. Power supply and clock circuits provide stability and synchronization. Communication interfaces like SPI, I2C, UART for data exchange. Microcontroller means a compact integrated circuit designed to control a specific function. CPU, memory, input, output ports, timer, communication interfaces are the key features. PIC, AVR, ARM, Cortex, ASP32 are the popular microcontrollers used. Microcontroller architectures. First we studied about the Von Neumann architecture. It's a single memory for a program and a data storage, sequential instruction execution, simple design but slower due to a memory bottleneck. Then Von Neumann basic structure as shown in the block diagram. Next we should study about the hardware architecture. It has a separate memory for a program and a data storage, parallel instruction execution, faster performance commonly used in embedded system. The hardware architecture as shown in the block diagram. Next, MPLAB IDE. MPLAB IDE is a compressive development tool for a PIC microcontroller. It has a XCS compiler. It's an AC compiler for a 8-bit PIC microcontroller. PICSimLab simulator, a tool for simulating the PIC microcontroller project. By using these tools, we developed a microhardware project. It will be shown on last. PIC16F877A microcontroller overview. It has a 8-bit RISC architecture, 33 in-out pins, multiple timers, ADC, SPI bar 12C, and UART. Applications are like motor control, industrial automation, and sensor interfacing. Peripherals used in these projects are like switch, keypads, CLCD, display, timers, and buzzer. GPIO means General Purpose Input Output Ports. Pin mapping for PIC16F877A, configuring digital and analog inputs or outputs. Tactile switches in an embedded system. Tactile switches are mechanically switches that provides a physical feedback like when pressed. When pressed, the switch closes the circuit and registers an input signal. Used in control panel, remote controls, and industrial automation. Configuring GPIO pins as digital inputs and detecting button presses. Matrix keypad interfacing. A matrix keypad consisting of rows and columns forming the multiple input keys in a compact design. Working principle: each key press completes a circuit between a specific row and the column. Scanning method: using row and column scanning techniques to detect the key press. Applications used in ATM machines, security locks, and industrial control panels. Interrupts in an embedded system. Interrupts allows in microcontroller to respond to external or internal event immediately. Types of interrupts are like external interrupt, internal interrupt, interrupt service runtime. External interrupt, triggering by external events like button press or sensor output. Internal interrupt are like triggering by timers, ADC conversions, or communication models. Like ISR are a specific function that executes when an interrupt occurs. Applications are used in a real-time application like control, sensor monitoring, and automation. Timers in an embedded system. Definitions: timers generate time-based delays and event triggers. Types of timers like timer mode, counter mode, and interfacing with PIC 16F877A. In a timer mode, counts clock cycles and generate perceived delays. In a counter mode, counter external events such as pulse from a sensor, and in a interfacing with PIC 16F877A, it's like using timer 1, timer 2 for different applications. In applications used in a motor speed control, periodic data logging, and signal generating. Prescaler and postscaler in a timers. Prescaler divides the input clock before feeding into the timer. Postscaler divides the time overflow output before generated an interrupt. Significance: helps achieve precise timing intervals without requiring high-speed clocks. Example implementation: configuring prescaler values in timer to achieve a different delay duration. LCD interfacing embedded system. An LCD is used for visual output in embedded system. LCD means liquid crystal display. This has a 16 into 2 character LCD, 128 into 64 graphical LCD. The common type of LCDs. Interfacing with Picha, using 4-bit and 8-bit modes to send data and commands. Applications are like used in embedded GUIs, industrial displays, and monitoring system. Key learning: embedded C programming proficiency, writing optimized firmware for microcontroller, hardware interfacing skills, working with switches, keypad, timer, LCDs, and actuators. Debugging and trustless shooting, identify and fix hardware or software issues. Real-time application development, implementing hand-on project with PIC 16F877. 1to-C communication in an embedded system. 1to-C is a two-wire communication protocol. How it works: uses STA and SCL for synchronized data exchange. Addressing systems are like 1to-C bus as a unique address. Application used in EEPROMS, temperature sensors, and a real-time clock. EEPROM: electrically erasable, programmable, read-only memory. Definition: a type of non-volatile memory used for storing data. Retain data even when power is lost. It is the features. Interfacing with PIC 16F877A, using 1to-C bar SPI to read and write data. Applications used in the configuration, storage, data logging, and firmware updates. Watchdog timer in an embedded system. Definition: a time that resets the system if hangs or crashed. Importance: prevent system failures and ensure readability. Configuring in PIC 16F877A, enabling the watchdog timer, setting timeout period, and clearing watchdog periodically. Applications used in the industrial automation, medical devices, and crucial system. Micro oven project. We finally built a micro oven project at the end of this internship. Project title is a micro oven with an embedded control. Objective: to design and implement a microcontroller based micro oven control system. Microcontrollers used is PIC 16F877A. Components used keypad, LCD display, buzzer, relays, heating element, fan, timer module. One project working principle: user input, time and power level selection via matrix keypad processing. Microcontroller manages timer, relay and heating element. Output display cooking status and countdown on a 16 into 2 LCD. Safety features: buzzer alert for a overheat protection. Cooling system: a fan control mechanism ensures even heat distribution. Future scope and enhancement: IoT integration, enabling remote control via mobile applications. Touchscreen displays replacing the keypad with a graphical interface. Smart cooking algorithms, AI based time and temperature adjustment. Energy optimization, efficient power management for reduced consumption.
Before you see the project demonstration, let me open MPLab ID. So where I wrote the code for the microwave oven using multiple source files. So this project consists of so many files. So before you see all the files, let me give a brief introduction of the files which I have used. One is main.c and main.h, where are source file and the header file. So which handles system initialization and peripheral setup and the main control loop. And the microven.c, microven.h, which manages the core functionality of the microwave oven, including mode selection and process execution. And clc.c and clc.h, which controls the LCD display, handling messages and status updates. And we have isr.c, which is implements interrupt service routines for safety mechanisms and real-time operations. And I have matrix keypad.c, matrix keypad.h, so which processes user input from the keypad, allowing selection of cooking modes and time adjustments. And we have timers.c, timers.h, which manages countdown timers, ensuring accurate cooking durations. So now I will walk through the key sections of the code. So in main.c, the microcontroller is initialized and peripherals such as the LCD, keypad and timers are configured. The main control loop continuously monitors user input and system status. And in microven.c, the different cooking modes like micro, grill and convection are handled. Based on user selection, the appropriate functions are called to adjust cooking power, set timers and activate heating elements. And in the clc.c file, ensures that relevant messages such as like powering on microwave oven, mode selection and countdown timers are displayed correctly on the LCD. Interrupt handling in isr.c ensures safety by stopping the microwave if the door is open. So the timer functions in timers.c ensures precise countdown operations. So now I'll compile the code to ensure there are no errors. Once compiled successfully, the X file will be uploaded to the PIC16F877A microcontroller. After uploading, the system is now ready for demonstration, right? Right click on that micro one, select the clean and build. Then the output will be appearing like clean successful if there are no errors. Then even we'll be getting a warnings, but we can neglect those because at the end, if you are getting build successful, if it is build fail, then those warnings, those error you need to clear, you need to rectify. But now the project is built successfully. So once we compiled successfully, the X file will be uploaded to the microcontroller, that is PIC16F877A microcontroller. So now before I upload my microwave oven project code, let me first introduce you to PICSimLab, the simulator which I am using in my project now. So why use a simulator actually? So when developing embedded systems, testing directly on hardware can be difficult, and even there's always a risk on the damaging components, right? And even debugging can be a time consuming. So that's where PICSimLab comes in. So it is an open source simulation platform that allows us to test, debug and refine microcontroller based projects without needing any physical hardware. So what is this PICSimLab? So PICSimLab is a microcontroller simulation environment that emulates different PIC microcontrollers like the PIC16F877A and PIC18F4520, which are commonly used in embedded systems. So with this, we can test our embedded C code before flashing it onto a real microcontroller. And even we can simulate peripherals like LCDs, keypads, buzzers, and relays. And we can debug errors safely without damaging real components. And even we can quickly modify and test code without rewiring circuits. And we can also analyze circuit behavior and verifying logic before deployment. So using Pixim Lab, I can show you how the microwave oven works step by step, just like a real hardware prototype but without needing a physical setup. So now let's take a closer look at this simulator and find its different parts. First, if you see top left, that is green screen area, which is called LCD display, liquid crystal display. So here this is a 16 cross 4 character LCD based on the HD44780 driver. So it is used to display system messages. And next, bottom left, number pad 1 to hashtag. So those are all called matrix keypad. This is a 4 cross 4 matrix keypad acting as the user input interfaces. And next, middle section, you see small red lights. So those are all LED indicators. So the LED represents different status indicators. And next, top right, near fan and heater labels, if you see, those are all called cooling fan and heater. So the fan is simulated here to show how the microwave cools down after operation, and the heater turns on during cooking and it is linked to the selected power level. And right side, two large white blocks, relays. So these simulate the real relay switches that turn on or off the microwave heater and fan. So when I press start, the relay activates, powering the heater. When I press stop, the relay cuts off the power supply. And next, near the fan and heater section, we have the buzzer. So this works as an alert system. It sounds when cooking starts or stops, when the cooking time finishes, when an occurs like. And next, bottom right, we have black IC labeled PIC 18F4520. So that is a microcontroller. So this is the brain of the entire system. So it runs the embedded C code that I have written in MPLAB IDE. It processes inputs from the keypad, updates the LCD, controls relay, and ensures safety mechanisms work properly. And next we have bottom right, blue button labeled reset. Yes, so if something goes wrong during simulation, I can press this button to reset the microcontroller and restart the program. That is a reset button. And next, middle right, we have LM35 sensor. So it is a temperature sensor. So this is also we have used, and we can also use in real world applications for automatic temperature based cooking, but here it's simulated just for a display. Now it's time for the demonstration. So let's begin. So first I load the X file into the simulator. To do that, I'll click on file, then select load X. Here I'll choose the microoven.hex file and click on open. So once the file is loaded successfully, the simulation will begin. Now let's observe the CLCD, character LCD. The display will show the message powering on micro oven. So after a few moments, the screen will update and display the 4 available modes, cooking modes, which are like micro mode, grill mode, convention mode, start mode. So to select any of these modes, I'll use the matrix keypad. So let's say I want to enter micro mode. So I'll press the corresponding key on the keypad, which in the case is 1. So once selected, the LCD will display with the default power level of 900 watts as programmed in the code. So next, it is asking for to set the time. So using the keypad, I need to enter the time in minutes and seconds, right? So I want to enter the time limit of 10 seconds, 1 minute. So I need to press 1, then 0, then again 1. And here you see that star for clear, hashtag for enter. Star for clear in the sense if If you pressed any other number, unfortunately, like if you want to enter 2 minutes, but you have entered 1 minute there. So to change that, we can have the option to clear it and again to re-enter the time. So if you are confirm and you are done with the entering the time, we need to press the hashtag enter. So after that, it will start the microwave and the system will activate and the fan will begin operating while the countdown timer starts, as you see there. So the LCD will continuously updating, right? As you see the timer there. So showing the remaining cooking time. And now we can demonstrate the pause and resume. As here you see 4, 5, 6 options like that. Start or resume, pause or stop. So I will demonstrate the pause and resume functionality now. So pressing the pause will stop the countdown. And again you can press the resume, which again restart the timer from where it was paused. So let me press the button 4. So see, there it restarted the timer from where it was paused previously. So let the countdown complete. But in between, if you want to stop the microwave manually, so we need to press the stop button there. So the LCD will return directly to the main menu, allowing the user to select a new mode or set a new timer there, as you see here. Now if we go for the grill mode, so we need to press the button 2. So same like the micro mode, inside we need to set the timer. For example, I need to set the time for just 10 seconds. Say I need to enter 1, then 0, then hashtag, that is to enter. So again the system activated and the fan will begin operating while the countdown timer also started. So let the countdown complete. Once the timer reaches to 0, the LCD will display C, time up, enjoy your meal. And again it is coming to the main menu. So now let's go for the mode convention, that is the third mode. So for that I need to press 3. So after pressing it, it is displayed like to set the temperature in Celsius. So let me enter the temperature 120. So 120 and press hashtag. So now you see here it displays preheating with a default time limit, that is 1 minute, that is 60 seconds. So I let the countdown complete. So once the timer reaches to 0, it display the message to the user in the interface LCD display, that is time up, enjoy your meal. So now it return back to the main menu, and if you go for the start last mode, if you click on that, again it starts the timer with the limit of 30 seconds, and again the below done will be having an options to resume, pause, stop. So same operations which you have done in the previous modes, that is micro mode, grill mode and convection mode. So the fan will be operating while the countdown time starts always. So once it is done, it will display time up, you can enjoy your meal. So this is how my project works. So I concludes my demonstration of the microwave oven project. So this system successfully handles real-time cooking control, safety mechanisms and user interaction. So there is a chance for the future improvements could include like IoT integration for remote control and AI based cooking adjustments like that. So I'm very much thankful to all of you who have watched with so much of attention and patience. So I'm very much thankful to everyone. Thank you.